Good morning, good afternoon, or good evening, everybody, and welcome to the first webinar organized by Karen today during BTS. This webinar is Test Your Knowledge on Natural Refrigerants, where we hope that you learn something new about natural refrigerants apart from testing your knowledge. My name is Miriam Solana. I work in the Knowledge Center of CAREL, and I am here with my colleague Biagio Lamanna, and we two will give the whole webinar. I give the floor to my colleague Biagio Lamanna to introduce the Knowledge Center of CAREL with a few words before starting with the agenda of the session.
Thank you, Miriam. Hello, everybody. I'll just stay on one slide on our Knowledge Center to show you what we do. The Knowledge Center of CAREL is managing the competencies and expertise in our company on the different applications in the air conditioning and refrigeration market of our products and solutions. We basically do this through three main activities. At first, being partners of many different stakeholders and members of different associations worldwide, we participate to the different lobby and networking activities, trying to, let me say, design and foresee the future scenarios concerning norms, regulation, and standards. Then we concentrate on the research activities in our thermodynamics laboratories. Here we test technologies, components, compressor, heat exchangers, and refrigerants, of course, developing our solutions and our expertise. As an example, in the last 10 years, we focused many projects on natural refrigerants, basically on propane, CO2, or ammonia. And as a last part of our work, we support our group and our customers with many different divulgation and training activities, like this one as an example. So participating to the different international meetings as speakers, of course, or producing white papers and writing blog posts on our blog. Today, we are in an example of support activities through divulgations, and Miriam will explain how this webinar works and the different contents.
Yes, this is the agenda for today. First, we will start with the quiz. There will be 8 questions with 3 possible answers, and only one is correct. So we will read the question. Then you will have some time to answer, around 30 seconds. And then we will comment the results, and we will explain the answer and something related with that answer. During the second part, we will present the white paper that we have recently published on natural refrigerants. And during the third part, we will answer the question that we have received through the inscription form, and also the ones we will receive during the presentation. You have the window question and answer in the part down of the presentation, and you can put the question, and I hope we will have time to answer them at the end. So let's start now with the quiz. This is the first question. Which safety group ammonia belong to? This question has a very short answer, so you will have just a few seconds to answer this question. Please.
Yes, you can see on the screen, so it's pretty easy. There are not so many choices, so yes, 40 seconds for all of you. You are receiving all the answers right now, real time. A few seconds more. Good. Come on, last ones. Thank you. So I can share the results just to let you know what are your answers. At the moment, you know, the most common answer is B12. Let's see with Miriam if this is correct.
So, very good. The answer is B2L. So most of you knew the answer. And ammonia belongs to this safety group because it's slightly flammable and toxic. Here you can see the parameters that determine if one refrigerant belongs to flammability and toxicity class or to another one. As regards flammability class, you can see the table on the left. There are 4 parameters. The first one is flame propagation, that is measured at 60 degrees Celsius and atmospheric pressure. This is the parameter that determines if one refrigerant belongs to group 2 or to the other numbers of flammability. The second parameter is the maximum burning capacity. That would be the speed of the flame if there is a flame propagation. And this is the parameter that differentiates A2L refrigerants from 2 refrigerants. Then we have a lower flammability limit and heat of combustion. And here in the table, you can see the values that determines if one refrigerant belongs to group 2 or group 3. As regards toxicity, you can see in the table on the right that the parameter is the occupational exposure limit. That is the allowable concentration that is acceptable in a workplace, in a concrete material. And for the refrigerants belonging to class A, this value is higher or equal to 400 ppm. And refrigerants like ammonia that belongs to group B, this value is lower than 400 ppm. Before going to the next question, just to highlight that a refrigerant that belongs to class A1 can be ignited at temperatures that are higher than 60 degrees Celsius, for example, during an externally fueled fire. So now it's time to go to the next question. The next question is, which ones among these temperatures and pressures could correspond to the evaporation or propane in a refrigeration circuit? So let's switch now to propane. Here you have the 3 possible answers. You have a few seconds to answer, right? Yes. And please, you can start now. Propane circuit, and then we will see some details about propane cycles and
refrigerant, yes,
thermodynamics. Just a few seconds, I would say.
Yes, nearly 30, 40 seconds for each question. So I will stop right now and I can share the results with you. So again, most of the people answered 2.4 bar G at -10. And yes, I can also confirm that it's the right answer to the question. So, sorry, just focusing on propane, as I said, at -10, the evaporation pressure of propane is 2.4, actually it's 2.44 bar G. To comment, to provide some quick information about propane, at first, if you look at the cycle, propane is a subcritical cycle. So in the end is pretty similar to, it's similar to all the other cycles that has been traditionally used with HFC refrigerants. Moreover, the pressure values between evaporator and condenser are not so high. So on the condenser, we have in this example 13 bar G to introduce some pressure related issue, and is not so low to prevent propane to work in low temperature application. In fact, one of the most common application of propane nowadays are chest freezers for ice creams or frozen foods. As a last hints about propane, we can see from the chart that being a pure fluid, it has no glide. So basically, both evaporation and condensation transformation are happening in an isothermal condition without considering the pressure drops, of course. If you would like to compare propane in a chest freezer application, so at -30 temperature degrees, I draw this table to compare it with some traditional refrigerants like R404A or R410A, other natural refrigerants, and other low GWP refrigerants that are in the market right now. At first, I highlighted the pressure of propane that, as I said, is in between low pressure refrigerants, like HFOs, that they cannot work actually in this application because the pressure is too low, and high pressure refrigerants like 410A or CO2. As a second point of interest, we can have a look on the comparison between the enthalpy differential in these conditions of the propane. In this case, a higher enthalpy differential means also higher efficiency. This is the reason why propane, in general, is an efficient refrigerant compared to most of the others. And then the last interesting thing is that the critical temperature of propane is pretty high. This allows propane to condensate at higher temperature compared to other refrigerants. And this is particularly useful when you are in a heat pump application, so in a heating application, where you can condensate and so produce, as an example, domestic hot water, sanitary hot water at higher temperatures without additional heating systems. So this is the reason why propane is a refrigerant that can be used for many purposes in many different applications, both in heating and cooling. Now it's time for the next question, Miriam. Thank you.
So the question number 3 is, why many propane refrigeration systems have been designed with more than one circuit? So we continue with propane, and let's see which are the answers and which one is the correct one.
Yeah.
Just a few seconds again. This is a different type of question.
Yes, this is related to efficiency or regulations or whatever. So let's see what's the typical knowledge of our audience today. 10 seconds more, just to let most of you to participate to this poll. Good, thank you. And here it is the result. So most of you did answer that is related basically on regulations and to maximum charge of the refrigerant per circuit, but not all of them did answer the same. So please, Miriam.
Okay, yes, this is the correct answer, that they were designed to comply with the refrigerant limit for a single circuit, because the standard 6335289 that is applied for commercial refrigerating appliances with an incorporated or remote refrigerant unit or compressor included applications with a refrigerant share up to 150 grams of propane. So it was thought that the best way to increase the cooling capacity of a system was to project different circuits for the same system. Here in the screen, you can see an example of this kind of systems where typically they have 3 circuits, but they can have more than 3 circuits or 2. But usually they have the 2 heat exchangers in common. You have here the condenser, here the evaporator, and then for each circuit there is a different expansion valve and a compressor. This standard has been updated, the international version of the standard. Now in 2019 it was published, the edition 3, and now the refrigerant share limit changed from 150 grams to 13 multiplied by the lower flammability limit up to 1.2 kilo of refrigerant. In the case of propane, this means 500 grams of propane, so the share now can be increased. But there will be additional requirements if one uses more than 150 grams of propane. You can see here an example that is the test that have to be carried out if one includes more than 150 grams of propane. And here in the picture, you can see the appliance from the front of the appliance and from the top. So it is interesting to see the appliance from the top, because we have sensor not only in the appliance, in the corners of the appliance, but we also have a sensor in the back and another one in the front. So now we are going to measure also the concentration of the refrigerant in the surroundings of the appliance if there is a leak. So this will be very important and will determine how they will be designed the system with propane in the next year. Just to highlight that this standard has already applied in Australia, New Zealand, and South Africa. They have updated their local standard to be in line with the international version, with edition 3. And in the next months, in the next year, we will see this the rest of the countries, the standard in line with this one, or maybe with some modifications. Okay, let's go now for the next question. We still with the international safety standard, and now let's see what international safety standard specifies safety requirements for heat pumps with propane. So you have 3 numbers in the answer, and let's see if you have that numbers in the head or not.
Yes, that's definitely a period in the last 5 years in which all the international standards for refrigerants or for safety are influencing so much the design of the air conditioning or refrigeration applications. So yes, the knowledge has been even more important than maybe in the past.
For sure.
Okay, here we are with the results. There is more people that answered 240, while there are some others that are thinking about 224 or 234.
I think we have a very expertise public today.
Yes.
This is good news.
Good news for sure. So yes, we have the same reference that has been mentioned by Miriam. So it's the IEC 6335, and in this case, for heat pumps, air conditioning in general, we have the /2/40, that is the one dedicated to safety requirements. Even here, we have 3 editions, okay, that are that is on the market, okay. The most commonly used by any country is edition 5. That is in force in most of the countries, while edition 6 has already been published a couple of years ago in 2018 and has been adopted just by Australia and New Zealand, but is on the road of adoption by almost all countries. However, we need to notice that we have an edition 7 that is on the road. This edition 7 has been voted and need to be published by the end of this year or beginning of next year. You know that it's not always an easy process and publication can be delayed. Looking at the flammability requirements, we need to notice immediately that for these air conditioning markets, higher charge of flammable refrigerants, and in particular propane, are allowed since edition 5. Edition 6 did add special requirements for the A2L refrigerants. We are talking about synthetic refrigerant that have some more mild requirements, being, into a flammability class that is lower than propane, and have some other mild requirements in terms of electronics. If we focus on some examples, we can focus on the edition 7, where we have even more possibilities to increase the charge, in this example of propane, in a single circuit, thanks to design feature of the application and surroundings. In particular, I'm taking as an example a room of about 20 square meters with standard ceiling 8. And you can see here from this list that a standard split system can reach up to nearly 350 grams for that room size, but can also rise this charge limits with a robust design and enhanced tightness of the units, or with a sufficient airflow that is in the room and incorporated in the unit itself with leakage detectors, and can reach up to 1 kilo of propane inside the circuit with the adoption of shut-off valves that can cut the circuit and reduce the amount of leakage per single area. As a final limit for indoor application, a propane unit can contain up to 5 kilos of refrigerant. Of course, it depends on the kind of environment and size and characteristic in which the unit is installed. Please note that for outdoor application, there's no limits. So outdoor application with propane can have a single circuit with as many kilos of propane in terms of standards, let me say. Of course, you need to take care about surroundings as usual.
Okay, let's go to question 5. In a transcritical CO2 systems with 3 valves, which is the valve that draws gaseous refrigerant directly into the compressor suction to avoid the pressure of the receiver to rise too much? So now we switch to CO2. This is a long question with short answers. So just a few seconds.
CO2 design is always, you know, interesting because it added to the traditional system many different new components, and so even the related question needs to be more, you know, detailed. Yes, complex. 10 seconds more to let most of you provide your answer. Okay, the poll is closed. Share results. So many different experts here. They talk about the flash gas valve. And so Miriam, let's see some details to explain how it works.
Yeah, it's the flash gas valve that is open when the pressure of the receiver is too high. And let's see how this kind of diagram works. This diagram is the evolution from the traditional diagram for the CO2, because when we work with transcritical CO2 at transcritical conditions, apart of having the gas cooler that is not condensing the CO2 but cooling it, it's very important to control the pressure of the gas cooler. So we don't have to control only the superheating like in the rest of the systems at subcritical conditions, but we also have to control the pressure of the gas cooler. And this is why this kind of system was designed. On the one hand, we have the high pressure valve that controls the pressure of the gas cooler. On the other hand, we have the expansion valve to control the superheating, and the third valve, that is the flash valve or RPRV, that is open when the pressure of the receiver is too high due to the work of the other 2 valves. On the right, you can see the pressure enthalpy diagram of this kind of configuration. You can see the gas cooler, then the high pressure valve, the receiver. From the receiver, the CO2 goes to the expansion valve, except when the pressure of the receiver is too high and the refrigerant goes to the flash valve. But here in the diagram, you can easily see that we are doing an expansion and then a compression without having any function, this refrigerant. So we can avoid this expansion compression in order to optimize to increase the efficiency of the system. And this is why the parallel compression systems were designed. If you look at the diagram on the left, you can see that we have the same components as before, the 3 valves, and we have added a set of compressors that where the refrigerant arrives directly from the receiver. We still have the flash valve because sometimes when the climate conditions when it will be colder, maybe it will not be worth to turn on the parallel compression, and the system will work as a 3 valve system. If you see the pressure enthalpy diagram, we have starting from the high pressure valve and the receiver, we see that the expansion compression we had before, we don't have it anymore, and the parallel compressor is compressing the CO2 from around 35 bar G instead of from around 25.5 bar G, And so we are avoiding these 10 bars of compression, increasing significantly the efficiency of the system. Okay, still CO2. What is an ejector? This is the sixth question. Three different answers.
In really few minutes, we are trying to describe the evolution of the circuit of CO2 that I guess it took about more than 10 years to establish as a diffuse knowledge, let me say, not of course in all the countries, but it took a while
Yes.
to make everything work.
Yeah, because it has been and significantly technological advance.
40 seconds. There is a, sorry, I waited just a little because there was, a couple of questions that are, rising and dropping
like
the first position. Yes, a competition between the first and the second. I can share the results with you. So two answers, were given by this question mainly, one related to high pressure, one related to temperature. Well, if we consider propane, CO2, the ejector exploits an effect that is called Venturi effect that is, based on the Bernoulli equation. This effect exploits the potential energy of the high pressure fluid, in this case refrigerant, and in this case CO2. So it's a pressure related effect. An ejector is a component that has two inputs and one output. If we concentrate for the first input, that is the fluid at high pressure that is coming out from the gas cooler, so in the same position of the high pressure valve, this refrigerant will enter the ejector and will cross a restriction here. So in the restriction, thanks to the Bernoulli law, we can explain the fact that while the velocity of refrigerant will increase really much, the pressure will decrease. And the design of this restriction is done to create a vacuum area after the restriction. The vacuum area makes, in the end, this ejector work like a refrigerant pump. So this vacuum is able to draw in the refrigerant from the second input that is coming out from the evaporators and bring it to a higher pressure that is the one used in the receiver. So it's a sort of vacuum pump for refrigerant. From a functional point of view, this device can work and behave like a compressor, so can rise the pressure between a lower value to a higher value. This has two main advantages inside the circuit. At first, it reduces the mass flow of refrigerant that is processed by the compressors. And this, of course, increases the reliability of compressors that have lower duty. Moreover, if you can look at the diagram, the pressure differential of the compressors that are working are the same described by Miriam before. So it's only between the receiver pressure and the gas cooler pressure. So the pressure differential is reduced compared to a typical system that is not working with ejector, and this saves energy. We need also to notice that the higher is the inlet pressure of the refrigerant that is coming from the gas cooler, and the higher will be the capacity of the ejector. This is the reason why ejectors are mostly used in hot climates where they can get the best benefits for the application. When the ejector is working with a lower pressure at the inlet, of course, it cannot create these vacuum effects, and in the end will behave exactly like the high pressure valve previously described by Miriam.
Question number 7. What is the natural refrigerant that is more widely used in condensing units? So now a question about the trends.
Here it is for you.
There are the three most used natural refrigerants in HVAC are applications, but there is only one that is the most widely used in condensing units.
Of course, we are concentrating on the natural refrigerants that we know that are the future. We are not considering the current market that is based on a mix between traditional refrigerants that are going to be phased down and some alternatives that are blends or synthetic refrigerant and natural refrigerants. Here we have opinion, of course, because there are some figures. Here we have propane and CO2 as the two most voted refrigerant, in particular propane. Here it is, the results for you. So Miriam, what about the current situation, example, in Europe?
So in Europe, the F-gas that was published in 2014 banned the refrigerants with the GWP higher than 2,500 for the stationary refrigeration units. And so it means that the most used refrigerant in condensing units are for 4A, cannot be used anymore from the year 2020 for last year. Considering the typical cooling capacity of a condensing unit and that the refrigerant share is quite high, CO2 seems to be the most suitable refrigerant, and it has been the most used so far for condensing units. I want to say as a curiosity that convenience stores are growing, about all in emerging countries. And so the market for condensing units is supposed to grow in the next year. Here I present two proposals of Karel for condensing units with our control system EQ. The proposal for medium temperature solution is the three valves diagram that I have shown before. You can see the high pressure valve here, the receiver, the expansion valve, and the flash valve. And the diagram is in the different position of the one I have shown before, but is the same design. For low temperature application, we have the same diagram, but instead of having the high pressure valve, we have an additional compressor. So we have two compressors, and we use the gas from the receiver to cool the gas that comes from the first compressor. Of course, this application can be also done with a dual compressor, because we have to the pressure differential higher than with the medium temperature application, of course. Okay, so let's go now for the last question of the quiz. How electronic expansion valves bring energy savings due to adaptive optimization of compressor operating parameters? Again, three different answers, now different topic. But efficiency is very important when we use natural refrigerants.
In general, I mean, the goal of natural refrigerants is to reduce the direct impact of our business, let me say, on the environment. And on the other hand, we have the indirect one that has the same goals, so to be reduced, and efficiency is pretty important for that.
Different answers?
Yes. I wait a little because people are,
Are still answering?
Yes. But unfortunately, we have limited time today, so I need to stop it and share the results. So here we have a majority that is answering that is related to the lower pressure differential on compressor side, and basically given by the condensation, and I will show you why this is true. So, electronic expansion valves are well known since many, many years as really good superheat controllers, and this is actually true. Valves can control superheat in a stable way at pretty low values, such as 3-4 kelvins. That is effectively increasing the evaporator efficiency. And usually this can be given at around 5%, in the best cases 10% of energy saving if we compare the electronic expansion valves with the traditional mechanical devices such as thermostatic valves or capillary tubes. However, some people are not knowing or not fixing the idea that the benefits of the expansion valves are not only related to superheat control, but the fact that electronic expansion valves and of course controllers can adapt the valve regulation to any working condition is particularly useful when you would like to increase the efficiency of compressors. In particular, an electronic expansion valve can work with floating evaporation and floating condensation. When we are focusing on evaporation, of course, in most of the cases, especially in the refrigeration field, evaporation temperature cannot rise so much because it's given by the application. So if you need to control the frozen food temperature, you cannot rise the evaporation up to -25, -24, because you need to keep the proper temperature on the refrigerated bay. On the other hand, if you consider the condensation, the floating condensation temperature can be reduced between summer and winter, or between night and day, of more than 15, 20, even 30 Celsius degrees. This huge amount of difference between the different conditions can let compressor work with a pretty low pressure differential. And this is particularly true that is giving a definitely higher energy saving compared to just the optimization of the evaporator. And this energy saving reach peaks of even more than 30%, and 20% as an average in 1 year long period. So it's important to underline that these kind of devices are pretty flexible, and their goal is try to optimize the entire working of compressors and units.
Great, so the quiz finish here. I hope you have learned something new. And I would like to present the white paper Natural Refrigerant that we have published recently. You can, if you are participating to BTS, you can download it directly in our booth, or otherwise you can download on carel.com. Here you have the index of the content of the white paper. We have tried to cover all the topics related to natural refrigerants and high efficiency solutions to optimize the use of natural refrigerants. So if there is some time now, we can go to the question and answer sections, not without before giving us the link to the white paper, the one of natural refrigerants and other white papers we have published in the past years, and the link to the blog of Karel, where every week we publish a different post on these topics and other topics related to the company. Is there some time for question and answers?
Yes, we collected some questions in the registration form, so we have some of them. And if we have time, we answer to all of them. Otherwise, we will answer by email to all of you.
So the first question that we have received is which ones are suitable for heating applications? Which natural refrigerants are suitable?
Yes. Both propane and CO2 are suitable for heating application. As I said before, propane has the capability to work at pretty high condensing temperature, so can be used in heating mode for even sanitary hot water production, and in the application of household environment is suggested to use as a split unit. So you have the propane as an outdoor unit, and then you have, as an example, air to water unit, so water inside. Concerning CO2, CO2 has the really good properties in the heat exchange of the gas that is coming, out from the compressor. So you can exploit this capability, and is pretty well known that, as an example, in the Far East, in Japan, as an example, most of the sanitary hot water production is done by heat pumps that are using CO2 as a fluid. So it's a matter of the different market requirements and evolution. So yes, both of them are pretty suitable for heating application.
The next question is maximum charging limits for propane over 150 grams and type of new compressor for bigger charging capacity of propane. So we have explained during the presentation about the standard 60335-289 that I think is the one that is related this question, because it's the one with the limit of 150 grams. Now with the update of the international one, this limit will become 500 grams for propane. And there are already compressors available, in particular the scroll and rotary, that for this kind of application, they can arrive to 40-50 cc. And for air conditioning applications, they can also arrive to bigger capacities.
Yeah, so outdoor application, basically, as I said.
Of course, respecting the chair limit always.
Another question is, what is the natural replacement for R47C?
I think it's the last question because we are running out of time.
We try to, a couple of minutes. There is a natural refrigerant, but it's not a direct retrofit of R410A. R47C, like even R410A. So the air conditioning refrigerants are having at the moment A2L synthetic blends that are replacement. Even them, they are not retrofit replacement. So they need to redesign the units because of flammability. In terms of natural refrigerants, basically being an air conditioning application, the application in which R407C is mostly used, propane, CO2 and ammonia are suitable. Propane is the most similar one because it's similar characteristics in terms of pressures and temperature, while CO2, as I said, is particularly useful when you would like to have heating modes, and on the other side, ammonia in direct expansion can be used for cooling mode. I guess we have a very short time for...
Okay, I just have to thank you everybody for the participation, to all the participants. Thank you to SECO for the organization of BTS. And thank you also to our colleagues that are behind the camera that are making a great job today. And enjoy BTS if you are participating. And I hope to see you soon in another webinar or another live event.
Thank you so much by my side, and bye-bye. Have a good continuation of your day or night or whatever. Okay, thank you. Bye-bye.